Hello, Scott Manley here, and I'm with Peter Beck of Rocket Lab, and we're here to talk about Neutron and everything else that Rocket Lab is up to, right? How are you, Peter?
Oh, very well, thanks, Scott. It's great to
I'm
chat.
so glad to have you here. So yeah, earlier in the year, you ate a hat. How did it taste?
Yep, it was absolutely terrible. When you put a hat in a blender, like all of the volatiles in the process of making the hat are released. So when you pull the top off the blender, you just get this waft of chemical concoction. I don't recommend it.
I'll try not to do it, but I mean, there must have been some, some thought that there was a great experience at the end of it because you got to start building another rocket.
Yeah, well, look, I mean, at Rocket Lab, everybody in this company is measured, do what you say you said you were going to do. So there was really only one option when I had such a change of heart that you have to own it for sure.
So the whole team's on board with this thing.
Oh yeah, I
Yeah,
mean,
yeah.
who doesn't want to build a new rocket? I mean, this is a dream. Generally in your career, if you get to build one rocket, you count yourself lucky. But to get to do it twice, that's very rare.
So I kind of want to talk about how it's changed from earlier in the year because it was first revealed as this very simple, rocket, 8 tons to orbit. It had kerosene. It had a different profile, and then you came back earlier this month, and there was a lot of radical changes to it. So I'm actually kind of interested how the process worked. Did you start with the business requirements and come up with this basic design, and then you sent it to the engineers? And did they come back or did you contribute? I'm really curious how this got that way.
Yeah, look, so I mean, the first kind of rendition of Neutron was almost a ruse. Like we knew that was going to be nothing like that. But we weren't far enough down the design process to be able to put out what we really felt was going to be the finished article. And also we knew it was going to be quite radical. So we thought, well, we'll put this we'll put out what everybody would expect, and then we'll finish our work and then release into a much greater detail. But really, how it all started is, as you point out, is it starts at the customer. And one of the advantages of flying Electron a bunch and building all those relationships with the customers is you get to know you get to know them super well, and you get to know the things that matter. And I think as people look at a rocket, often the mistake is thinking that the most expensive thing on the rocket is actually the rocket itself, and that is that is not the most expensive thing when you go to orbit. The rocket generally represents like one third of the cost when you go to orbit. It's actually all the overhead, all the infrastructure that surrounds a rocket that represents more of the value of it. So if you look at what we've done there, you see almost no infrastructure. You see no barge. You see no strong back, no breakover. All of these things actually add tremendous amount of cost. And I'm super fortunate to be the chief engineer on this project. So I can really this is really probably the last rocket I'll ever design. Who knows? But so it's been super liberating and fun process. But we all sat around a whiteboard, and there's a couple of fundamentals that I laid down, and probably the thing that drove the design the most was this rocket has to be turned around in 24 hours. Not because we actually want to turn the rocket around in 24 hours and fly it, but it drove that constraint drove a whole lot of decisions that ultimately resulted in the lowest possible cost to get to orbit. So that was kind of a key fundamental. The diameter and the shape are a consequence of reentry. So it all kind of started trying to do the mechanisms for the landing legs, and I spent weeks scratching around trying to solve that problem because look, mechanisms suck, and if you can avoid them, then that's always good. So it really Neutron in its current form was really designed in like 1 hour on a whiteboard fundamentally, because we all stood around the whiteboard and said, well, landing leads suck, so how can we avoid them? Well, let's just make the base wide enough so that we don't have to have them. And what we actually ended up with was like it was like a DCX. It was a traffic cone.
Yeah,
Um,
DCX, I remember that.
yeah, and it's not surprisingly that DCX ended up like it was because that was the most efficient design for a single stage to orbit. But for us, we had different requirements. One was no landing legs, so you end up with this really wide base. And then of course, your upper stage doesn't need to be the diameter of your base, so you end up with this taper. And then as we started evolving that design, the re-entry of that first stage drove more of the requirements than the ascent. And if you think about re-entry the 24-hour turnaround drove the ability to not launch on a barge. It drove the return to launch site concept of operations. Because marine assets, I don't know if you know, but marine assets are horrifically expensive to operate. Like, yeah, really, really expensive. It costs us way more to put one tiny little ship bobbing out in the ocean for Electron than it does for us to fly out there in a helicopter, do a whole lot of operations and come back, even pick up the stage. So, marine operations should be avoided at all cost. And so that kind of drove a lot of that kind of fundamental design. And then the upper stage is the highest performing stage that you need to produce. So putting that inside stage one and putting it all in tension makes it super, super light. So you end up with this kind of traffic cone design.
Yeah. So you said in the Neutron presentation that the upper stage on Neutron is the lightest upper stage ever. Does that mean it's lighter than the second stage of Electron?
Well, for its
okay, I was wondering if you meant that. I mean, I certainly understand that it's very light. Its structure, like its dry mass, will be very, very good.
Well, think for the upper stage. Think of Centaur, because the Centaur is another in-tension balloon tank hung stage, but except it's made of stainless steel, it's made of carbon, which is a quarter of the weight. So and the great thing about that is it's so light. There's no material in it. There's no material in it. It doesn't cost much. So all of these things kind of come together to make a lot of goodness.
So actually, yeah, there's the design of the rocket is to support re-entry, and you mentioned on Twitter this doesn't have a need for an entry burn to reduce the force of the atmosphere compared to, say, the Falcon 9. You believe that it can get away without an entry burn?
Yeah, so the thing is, the thing that unlocked return to launch site was really this, because you chew just a tremendous amount of propellant. So there's two burns. There's one which is the RTS-LS burn, which basically is a flip around and to set us back on the trajectory, and then there's a landing burn. You might go, well, how are we getting away with that? And the thing is that re-entering Electron has taught us so much. It's taught us, firstly, how to control a stage during re-entry just with coal gas RCS and some tricks to basically control that stage during re-entry. And it's taught us that if you can control that well enough through that corridor, then you can really define and constrain your heating to where you can protect a relatively small amount of the launch vehicle. Now with Neutron, if you look at it, it's got a very high ballistic coefficient, very big base, and it weighs nothing. So, if you're going to go and jump off the roof, it's kind of like jumping off the roof with an umbrella. It's because it's so light and it's so wide in diameter. Just like Electron, we let the atmosphere do a tremendous amount of the work, and we don't have to basically cook it because the deceleration profile is so light works to our advantage.
And there's aerodynamic features on this for your steering, I presume, right? You've got the fins at the front, or canards, depending. I mean, when they're actually in use, they're not canards.
Oh, that's right. That's exactly right. Yeah.
And then you've also got the legs. Two of them extend upwards as strakes along the side, and are those designed to provide lift?
Correct. Yep. So that's a kind of our downrange targeting lifting body, if you will. They also serve very useful raceways.
I was going to ask about that.
Yeah. So, the upper stage, because there is no strong back, that means there is no umbilical tower. So everything's umbilical in from the base, which means the upper stage fill and drain lines run up those raceways to to interface with the upper stage.
So will the umbilicals be in the side of the base? Because you know that's your heat shield on the bottom. It would seem the
Yeah.
best place. Yeah. Okay. And so the legs come down. I presume they can't be carbon fiber because they'll be getting a lot of heat from both entry and the rocket exhaust. You're going to have some metal components there.
Yeah. But I mean, the majority of the structure is still carbon. It's just we run a hot skin on the carbon.
Right. Okay. And the fins, will those have to be metal?
No,
No.
they'll all
No.
be
Okay.
carbon.
Okay. Um. So yeah, and the legs, they must have some sort of shock absorbers in it, right?
Correct. Yep. So there's basically a small section of the legs, about 500 millimeters, that are shock attenuation for the landing base.
So let's talk about the engine because obviously Archimedes engine, it's Rocket Lab's first like actual turbopump based engine. Again, are you excited to work on this?
Yeah, I mean, I know everybody gets excited about engines, but I'm trying to build the boringest engine there has ever been. So, I mean, the engine from a technology standpoint, the engine on Neutron is not exciting, and it's meant to be not exciting. And if you look at the propellant combination and the cycle, this is all about margin. It's all about margin. And designing a rocket is a giant engineering compromise. And you have to decide where the pain is going to be. And if you have heavy structures, then the pain is in the engines, and you end up with engines that are just really really pushed. If the pain is in the structures, then you can kind of simplify. Now, for us, we've only ever built carbon structures. So for us, the pain is not in the structures.
Well, I mean, because I say that because it struck me that while the Rutherford engine did a lot of radical and new things, it felt to me like an engineer actually an easier problem to solve than designing like a turbopump.
Oh man, no. But like the Rutherford is a screamer. It is like the combustion efficiency of that engine. It's really hard to build a really high efficiency small engine. It's also when as you push the efficiency up, the thermal constraints become higher and higher. And Rutherford, the smaller kind of the area, the higher heat flux per millimeter squared you actually have to deal with. Whereas a larger engine, you have much more margin on cooling. So Rutherford is actually a really tricky engine, and because it's an all Inconel engine, it doesn't have a copper liner, and it's so high performance. That engine is actually really really tough little engine to perfect. Now, we've done enough engines to know that there's always a demon, no matter where you go. But a GG cycle, LOX methane, 1,500 psi of chamber pressure, like it's all just heaps of margin in everywhere. And ultimately, if you're trying to build a reusable launch vehicle, you don't want to be running up near the yields of shafts and turbo pumps and running throats white hot and all this kind of. You just don't want to be there. So that was the reason for the choice.
So you're going to have 7 engines in the first stage, 100 tons of thrust per engine. I presume you're going to have to be able to throttle that down a fair amount and control it quickly for landing.
Yep. That's actually the trickiest part of the whole propulsion program is that throttling range. So for the upper stage we have to throttle it quite a ways back because we'll exceed our G limits. And it's quite nice that the upper stage engine throttling requirements match pretty much exactly with the landing burn engine requirements from a throttle perspective. So we only need to get that right once.
Oh, so the second stage, I was going to get some more. That's an Archimedes engine. It's also going to have basically this pretty similar power head, I would imagine.
Exactly. Yep.
Yeah.
Exactly
Any changes to the throat diameter and nozzle for?
No, not at the moment. I mean, generally you do. Even though the Rutherford is essentially the same engine, there is a small a difference in the throat diameter in Rutherford's upper stage. So there'll probably be some small changes there, but largely it will be the same.
I mean, ideally, you'll be building more of those because you'll be throwing them away.
Yeah, yeah. And that's also a good reason to, follow a GG cycle, is that it's a very inexpensive engine.
So, for the upper stage, I'm presuming you're going to have it able to relight once it's in
Yeah,
orbit. So, how are you going to perform restart and ignition?
yeah. I mean, it's no different to, what we do with a electron upper stage. You have a start basket to contain propellants and a spin start on the GG. So it's nothing tricky
So,
there.
you're going to electrically start the gas generator?
We'll blow some gas over it.
Oh, okay. That's what I'm. And so the upper stage has to throttle down as well because if you've got the lightest upper stage and a light payload, 100
Yeah,
tons would be a lot of thrust.
it's actually, this is one of the hardest problems to solve. Actually, yeah.
I thought it was kind of oversized, to be honest. I was
No, it is.
like, I
No,
thought it might be a different engine.
it actually is. It is oversized. But the thing is that, like I said before, it's always a giant engineering compromise. It's awesome for gravity losses, just after staging, because you can sink all of that thrust in there. And the upper stage is just super efficient. If you look at the size of the upper stage compared to the first stage, it's really quite tiny, and that's because it's just so grunty and small. So you win on kind of negating the gravity losses at the start of second stage burn, but you lose when you have to throttle it back so you don't put the satellite solar panels through its battery pack at the end.
You're looking at this project going ahead. What's your biggest concern about switching over to methane as a propellant?
I just really the ground handling of it. Look, I've never subscribed to the fact that, well, if you've got one cryogenic propellant, you may as well have two. I mean, that's just terrible. Like, you've got to deal with one cryogenic propellant. Why on earth would you want to deal with two? It doesn't not easier at all. I mean, there's still a delta in temperature between the two propellants anyway that's not useful. So you still have to deal with all the same things you have to deal with a room temperature propellant. But really, what drove methane was reusability once again. So if you look at the timelines, and if you look at, like, from a LOX-Kira perspective, what are the things that take a lot of time to be able to turn a vehicle in 24 hours? Well, I mean, you have to descunge, decoke, and clean out all of the soots of a gas generator cycle, or even in the main TCA on a LOX-Kira engine. That takes a huge amount of time. Whereas if you run LOX methane, basically you can eat your lunch off the TCA and the GG exhaust. So it all came down to the 24 turning this vehicle in 24 hours. LOX Kero it'd be a fine choice, but it wouldn't meet that requirement. The servicing between flights of the engines just drives that away.
Cool. So, how are you going to pressurize the tanks?
Autogenius.
Okay, and you're not worried about like hot gases going in through your composite tanks?
Define hot gases. I mean, like room temperature? No, not worried about that at all.
Yeah.
If I was putting like 150 degrees Celsius gaseous oxygen in there, I'd think differently. But no, room temperature, warm, cold gas, however you want to define it, not an issue at all.
And so yeah, Rocket Lab has worked a lot with carbon fiber over the years, and I'm just curious. How is your work? How has this evolved since the Electron? I presume you've had changes to your process during the Electron program,
Mm.
and going forwards. I'm just curious if you get anything. Are there new techniques, formulations that are going to be needed for Neutron or?
Yeah, I mean, look, we've learned a lot, and we've learned a lot in so many areas. So, firstly, like laminate formulation, resin systems. It was always a really big challenge was going to be a really big challenge to think that could we have a composite system that would be happy at cryogenic temperatures and then happy at elevated temperatures when we re-enter. And we already solved that problem with Electron. And cryogenics and composites is a whole problem to solve with microcracking and interlaminar shears and bits and pieces. And then it's a completely different problem when you go and elevate the temperatures. So all of that is solved. And composite, I sort of said in the movie that composites get a really hard rap of being super expensive and slow and all the rest of it. And that's true if you're like, one dude in a clean room laying it down by hand. But when you're doing things like, automatic tape laying, if you've got machines like Rosie, man, it's fast. Like to lay down an upper stage in with an automatic fiber placement machine, you're talking like a day. And you're measuring the build time in meters a minute. Like it's super super fast and incredibly reliable and accurate. So things have moved a long way in the composites industry, from guys in a clean room hand laying down bits and pieces. So it's super super fast and really really cost effective.
Okay, and so how does that leave you if you do need to make changes during to the design? Like, how quickly can you turn
Yeah.
around?
So this is the engineering compromise, right? Is that so? If you wanted to iterate a design over and over and over and over again, composites would be the worst decision you could make, because the real cost in composites is the tooling. So it's very very difficult to build a tool and then completely scrap your design and change and iterate and iterate and iterate. But we tend to iterate at the kind of the component and subassembly level. By the time we're building structures, we expect that to be right. And if you look at our development approach, is it's not unique, but I mean, I kind of liken our development approach somewhere in between like the traditional ULAs and whatnot and kind of SpaceX. It's kind of in the middle. We have a fail fast philosophy, super hardware rich. We build lots of hardware, but by the time we get to like assembly level, we don't expect stuff to fail. Like by the time we're building tanks and rockets and bits and pieces, we don't expect it to fail. And if you look at like Electron, the very first Electron that we flew looks identical to number 23. There's no fundamental design changes that were made. We failed fast early, but once we had arrived at the design, then it's locked in.
There is a bit of a tank stretch in the latest, isn't there? Or is that a fairing, the fairing that gets stretched?
We put about 500 millimeters in the upper stage.
Okay.
And that's just, as Rutherford engines are getting higher and higher performance, actually, majority of that was given from batteries. Battery technology, as we predicted, was improving. So, we did a new battery program and it just gave us a little bit more performance, which, we're able to kind of eat some of the mass that we added for recovery and put us at a net neutral place.
So, I mean, I would imagine that given you've got a tapered design on Neutron, you couldn't simply stretch the tanks without getting a whole bunch of new tooling.
Yeah, most of the taper is actually in the interstage section, because it's such a wide vehicle. The tanks at the bottom, for stage one, are not far off spherical. Like they're these two big blobs of spheres down there. So if we needed to extend an increased tank, it wouldn't be that big a deal because it's in basically a parallel section. But yeah, a little bit of tank stretch here and there is no big deal. But if you're fundamentally, changing the design, then this is the trade that you make when you work with composites.
And actually, the Neutron design, does it use a common bulkhead or is it two separate tanks?
Yeah.
Okay, cool.
Yeah, no problem. Yeah.
And those tanks go right out to the structural wall, or
Correct.
okay, yeah,
Yeah.
just
But the majority, I should try and get you a section of it across, because the majority of it is actually interstage, versus tanks. Like because it's such a fat diameter at the bottom, that the tanks are pretty stumpy.
yeah. I imagine there's a fair amount of room in that interstage for the supporting hardware, right? I mean, you're going to have the fins that back onto that, right?
Yeah.
And
Yeah.
those will have electrical actuators, or
Yeah, I mean that's still in trade actually. Electrohydraulic or just straight electrical is in trade, because there's actually quite a lot of systems like that around the vehicle, because the upper stage is kind of hung off the payload plate, and the way that we hope to integrate that, and of course you've got the hungry hippo fairing.
yes.
So the trade right now is do we just do a electrohydraulic system for all of those, or do we put discrete electrical actuators on each one of them?
Yeah, I mean, and speaking of that fairing, obviously a lot of comments were made about certain links to James Bond. Right? And you know, you are in New Zealand, which I'm going to point out. I believe it has a lot of volcanoes.
A lot of volcanoes,
Great
correct.
places for a rocket base, right?
Yeah.
Do you have a white cat?
I do not have a white cat. No.
I'm sure somebody at Rocket Lab does. But
I guarantee it.
yeah, but yeah, I mean, it shows a four-part fairing, and that obviously this is an early design, and I'm wondering what the trades are for a four-part versus a three-part versus a
Yeah, yeah.
two-part. You know,
Yeah, yeah, yep, yep. So, and I would say that that is a hot topic in discussion at the moment, whether it's four part or a two part. Basically, what it comes down to is exit cone clearance. So, as the second stage is exiting, out of the interstage and clearing past those bearings, the four part gives you the most amount of clearance cone. But there are some nice little tricks with some oversender mechanisms that we're looking at that would enable us to do it with two. It's just, once again, it's the trade, the simplicity of only having two moving parts versus the complexity of a mechanism, or the simplicity of a mechanism but four moving parts.
right? Geometrically, the two-part has to go further out.
Correct.
But so why not three then? Because three gets you the same amount of motion, but
Oh, I like even numbers. So,
totally valid reason.
yeah.
You know, you could. I imagine there's like a bilateral symmetry in the rocket, so a four-way sort of fits probably with everything else.
Yeah, so the four pedals is actually a hangover from an earlier iteration where we were going to use those pedals as aero braking. And actually, the original concept that I really pushed hard to see if we could close was to use them as actually control surfaces, so we didn't have to have any forward canards or any actuated fin surfaces. But the shape of them is just super ugly, and they're not good aero surfaces, and getting any kind of tolerance out of them was, from a control perspective, was just a GNC nightmare. So sometimes it's easier to make control much simpler, given that control is actually one of the really hard things here. Giving the GNC team a break with some fins that they know what they're going to do when they actuate them is a nicer place to be.
Yeah, I would just imagine the amount of force you had to put through those to keep them still and stop them flapping.
Yeah, it was huge. Yeah.
Yeah, it's funny because somebody asked me about that, and I rejected the idea as silly. So I'm happy that somebody you thought about it.
Yeah, yeah.
So I mean, and that also, I would imagine that if they have problems where they can't close, will you have a way to eject those so that you can land a vehicle?
No, I mean
No.
that's a whole level of complexity we don't really want to have. I mean, at the end of the day, it's a simple pivot and a hydraulic ram. I mean, yep, everything can fail, but it's a pretty low risk system, especially given that the load on them is almost zero when they're being actuated from an aerodynamic and heating
Yeah, once
standpoint.
they're locked in place, I imagine there'll be latches between the segments and stuff because you've got to handle the ascent. And actually, I believe during the first Neutron presentation, you actually talked about possibly making this a human-rated vehicle. Yeah,
Correct.
and presumably in that case, it wouldn't have the fairing; it would have a integrated
Capsule.
vehicle on top.
Yep, exactly right.
And you could still use the existing second stage, but it would just be radically different. Would you be using that given the mass of human rated vehicles? Would that be an expendable launch, or you haven't?
I mean, you can get some people on orbit with 8 tons. I mean, look at Soyuz, for example.
Yeah.
So you can do some meaningful things with that. I mean, if you need more performance, there's options to trade. Yep, you can go expendable, or if you really had to, you could actually land on a barge or something downrange that would increase your payload performance a bit. But we think 8 tons is plenty to get 3 people on orbit.
Yeah, it's not a lot of leg room in a Soyuz, I'm told.
No, no.
But so that you said 15 tons if it was expandable, right? And while you say no barges, like there's presumably some value in between 8 and 15 that you could get from a barge landing.
Yep. We'll just have to look at at the moment that we're really kind of augured in on that 8 ton class. We think this is where we're seeing the majority of the interest from our customer base. So we think that's the right place to be. And if we found that we were wrong, we would probably stretch tanks before we would introduce downrange assets. But it's always an option.
I mean, I guess it's an option in that you wouldn't need a radical vehicle redesign to accommodate
No,
it. So if the business case worked out, you could start
yes.
renting barges or whatever.
I don't own ownership.
You
I just
don't.
do not. Like anybody who owns a boat already knows what owning a boat means. Like ownership is just terrible.
Yeah, I live in the Bay Area. There's a lot of that. So we've talked a lot about Neutron. It's really cool. Do you mind? I'd really curious if you want to talk about Photon because we're getting ready
Sure.
for
Yeah.
Capstone next year, right?
Yeah. Sure. Yeah. Love to.
Okay. Well, what is the current status like of Photon and Hypercurie?
Yeah. So I mean, it's getting really close. I mean, I'm not sure. I think we've released some images of the flight vehicle.
You released a
Um,
really good looking vehicle. It looks
yeah.
shiny.
Yeah. No, it's beautiful. It's all like to build beautiful things. So yeah, no, that's so it was going through the acceptance vibe test. Actually, right now, yesterday it went up on the vibe table. So it's just going through its final final TVACs and vibes and whatnot, getting ready for flight early next year. So man, that's been a big program. It has absorbed way more resources and time than we thought it was going to. That like going to the moon is no joke, as it turns out. That's proper hard.
Yeah, there's nothing like Photon out there with its interesting engine, I guess.
Yeah, I mean the Hypercurie engine is once again it's just super high performance for a tiny little engine. 320 seconds of ISP for this tiny little engine is right up there. If you look at all of the kind of the hypergoals and storables, kissing up in that 320-second range is rare.
But and your Hypercurie has pumps in it, right? Electrical pumps. Yeah,
Yep, yep.
and so that's partly why you can get that performance because you can get the higher chamber pressures.
And exactly. And like this is the perfect application of electric pumps because we have 8 burns to do, and in between burns we just let the sun recharge all the batteries, and it's like it's just the perfect symbiosis here because the sun is just you're just harvesting that energy from the sun. You're not carrying it in a pressurant tank or anything like that. It's just makes things so light and efficient.
I mean, imagine it's an extra complication for the navigators to try to figure out long enough between each burn to make sure you can recharge for the burn length.
Yeah, I mean, we've kind of sized solar, the panels in the to give us plenty of margin in that respect. The hardest thing with this mission, actually, well, I don't know the hardest thing, but everything is hard. But each one of those 8 burns, one of the reasons why there's 8 burns is because we do the burn, and then we use the FR light radio and do all the Doppler ranging from it to figure out where it is in the universe. And then, in 24 hours, the GNC team has to completely recompute everything again, and then we do another burn. And then the idea is just to keep refining that margin right down, and that increasing that accuracy right down until the final kind of TLI burn, which is hold on to your seat for that one. It's got to be just right. But it just but there's going to be no sleep for the GNC team for like 8 days as we do each one of these burns and recalculate its position, and it's quite a unique way to get to where we want to go here in really utilizing as much of the Earth and the Moon's gravitational field to get us in the right place. So direct inject is super energy intensive, but much simpler.
Well, and yeah, you're also going to NRHO, and that is one of these chaotic orbits. You're not like
Correct.
Apollo where you're just rushing across this hump in the middle. You're
Correct.
teasing your way through this like hole in space in the geometry.
Yep. Yep.
And so the plan with the you're going to deposit Capstone satellite, and then you're going to
Yep.
go your own way.
Correct.
And I don't haven't heard. Are there instruments that you're bringing, or is it just you know?
Oh, well, I mean, we have camera really,
It's
that's
an
about it. I
engineering
mean, and
camera.
yeah, yeah, and but we also have star trackers. So there's another couple of cameras there, but they're sort of 5 megapixel black and white cameras. But we have the Rocket Lab payload, if you will, is a camera. But I mean, there's a lot of other, like even just the ranging radio is a tremendous amount of learning we can do with that. And this is all sets us up for the Venus mission in 2023, because basically the trajectory is going to a different place, but we're using exactly the same process to get there.
Yeah, and I mean, presumably you'll have to work on the thermals of Photon before then for a Venus trip.
Well, they actually the reentry probe that we're kind of depositing in Venus is really the only thing that looks different.
Oh, okay.
Instead of being a CAPSTONE spacecraft on the top, there's a reentry probe.
Well, yeah, that's going to be great. I'm really looking forward to seeing this thing fly and what both missions send us back. Peter, this has absolutely been great to talk to you about all this stuff, and I no doubt have like a million other questions afterwards. But it's always a pleasure.
Likewise, no, always fun.
Yeah.